Hi to all. Today's topic is moving coil galvanometer. This is very important topic in class 12. Now I am going to explain what is this moving coil galvanometer and what is its use and everything I am going to explain. First of all, and this is very important for the exam. Okay, this topic, listen very carefully, and it is very easy. What is a moving coil galvanometer? A device used to measure small current or voltage is called as moving coil galvanometer. Moving coil galvanometer is a device that is used to measure the small current or the small voltage. Then its principle is what? On what principle it will depends. The principle is that a current carrying coil placed in uniform magnetic field experiences the torque and deflects. We know that whenever a current carrying coil is placed in the magnetic field, on the torque will acts, due to the torque that coil will be rotates, and then on that principle this moving coil galvanometer will works. Okay, let us see here. This is a north and south horseshoe magnet, two poles, and they are concave shaped poles, and in the middle there is a soft iron core is there. Around that there is a current insulated copper wire is wounded. Okay, and now one pointer is attached to the soft iron, that is over the circular scale. This is the circular scale. Then how it will works, let us see. And now when the current passes through this coil, at that moment, right, this coil is in the magnetic field. On the coil, torque will act. Due to that torque, this will be deflects. Like this. Okay, it will be deflect either clockwise or the anti-clockwise based on the direction of the current due to the torque. When this one deflects and it is pivoted over it is connected with a spring. When it is deflected, at that moment the spring will be compresses and the spring also tilts, and in that some restoring torque will be develops, and one deflecting torque will be this side will be there, and deflecting torque and some restoring torque also there. There are two torques will be generates, and when they are equal, this pointer will comes to rest. It will deflect and it will come to rest at certain position. Okay, then deflecting torque is equal to restoring torque. Here we are using the concave shaped poles and soft iron core. Around that the current carrying wire is wounded. Once again I will repeat the construction. It was very easy. Okay, the moving coil galvanometer consists horseshoe magnet with concave shaped poles, and in the middle of two poles we are placing one soft iron. Around that insulated wire is wounded. When the current passes through the insulated wire, then on the torque will act. This is attached to a pointer. That pointer will move on the circular scale, and when the current passes, then deflecting torque will act. Due to that it will be pointer will rotates, and if it will be showing some reading, some pointer, if it will comes to rest at certain position, at the moment the deflecting torque and restoring torque are equal. If deflecting torque, what it will do, it will try to rotate more, and that will act due to the current passing through the wire, and the restoring torque is it is pivoted over a spring. When it will be rotates, the spring compresses. Due to that restoring torque will be develops. When there is no current, then the deflecting torque becomes 0, but the restoring torque will be there. Then it will come back to its original position. Let us see here what is the deflecting torque. The deflecting torque on the coil. This is due to the current. Okay, the deflecting torque is due to the current. The deflecting torque formula is, we know already, the deflecting torque formula we derived when the current passes through a current carrying coil is placed in the magnetic field. On that the torque will act. The torque formula is NIAB sin theta. Okay, N is the number of turns, I is the current, A is the area of the coil, B is the magnetic field. The formula is NIAB sin theta. But here the radial magnetic field produces this concave shaped poles and the cylindrical soft iron. Soft iron is in the cylinder shape. Okay, they will produce the radial magnetic field. This magnetic field like radius. This radial magnetic field, due to the radial magnetic field, always these lines are parallel to the coil. Okay, the plane of the coil is always parallel to the magnetic field. When the plane and coil are parallel, okay, this is the coil plane, and when the magnetic field rotates like this, okay, then also always parallel. This is the magnetic field and this is the plane, and when they are parallel to each other, then this is the magnetic field. Area vector is like this there. That means when the magnetic field parallel to the plane, then we take the angle as 90 degree. Then the deflecting torque become NIAB. This is the maximum deflecting torque. Always the deflecting torque will become maximum. Okay. And the restoring torque is what? What is the restoring torque? Restoring torque is generates due to the restoring torque generates due to the spring, compression of the spring. Okay. The restoring torque is depends upon the formula is theta, c theta. If theta is the angle of deflection, here theta is angle of deflection. Angle of deflection. What is c here? C is the torsion constant, which I said. Torsion constant. Or another one more name is that restoring torque per unit twist. Restoring torque per unit twist. Per unit twist. What is the meaning of this one? For example, due to the deflecting torque, this coil will be rotates. Simply I will tell, for example, this is a spring. Okay, if you rotate like this, I am deflecting. This is the deflecting torque. I am rotating like this. Then when you left free, then it is going back. The reason for the going back is what? That is the restoring torque. I am applying the rotating force, that is the deflecting torque. I am applying the force, that is the deflecting torque. I am deflecting this one like this, but it is going back. Right, look at here. I am deflecting like this. When I will deflect like this, then when you left free, it is going back. That the torque which brings the object to its original position, that is called as restoring torque. And the torque that we are applying to rotate is a deflecting torque. Whenever current carrying coil is placed in the magnetic field, on that deflecting torque will act, then it will be rotates. Due to the torque, it will be rotates. Then the deflecting torque is that one. What is the restoring torque? Restoring torque try to bring the coil to its original position, right? And restore C is, this is the formula for the deflecting torque. Previously we derived in the last topic. And here the restoring torque is C theta, tau suffix D, deflecting torque. Restoring torque is tau suffix R. Here that we write as C theta. C is what? C is the restoring torque per unit twist, means per 1 degree restoring torque is C. For theta degree, this is rotated by an angle theta degree. Then what for the theta degree, what is the restoring torque? Then theta into C. That is the restoring torque formula is C theta. For 1 degree restoring torque is C. For theta degree restoring torque is C theta. Right? But at equilibrium, we know at equilibrium. At equilibrium, what we write? At equilibrium, that means, for example, the coil is rotated to certain position, certain angle. After that, it will comes to rest. The pointer is not deflecting further and not. Okay, actually for the galvanometer at the center it will be 0, it will be there, and this side deflecting torque and this side restoring torque, for example. Okay, and now at equilibrium, deflecting torque, rotating torque and restoring torque both are equal, right? At equilibrium we write deflecting torque. At equilibrium means pointer is at rest. Pointer rest means deflecting torque and restoring torque are equal. If deflecting torque is more, then the more it will rotates. If restoring torque is more, then it will come back to its original position. The original position is at the middle. At the middle, 0 will be there. Okay, right? Deflecting torque is equal restoring torque. Restoring torque. Let us write the values of that deflecting torque. What is it? NIAB, right? and restoring torque is what? C theta. From this we write the I formula as C by BAN into theta. This is the formula for the current. Okay. In this we write, this is equation 3. We can also write, but C by BAN we write as K. Okay. We write I is equal to, next step we write as I is equal to K theta. I is equal to K theta. Okay. This is equation 4. From this we write as I proportional to theta. I proportional to theta. The current, that means if you send the more current, if you send more current through the coil, then the more deflection will occurs. If you send the more current through the coil, then the more deflection occurs. Let us see here. The current here, it will flows like this. This is some current direction like this. Okay, in the coil some current will flows, and this is the direction of the current, either that side or this side. Okay, and now here what is K here? Which one is we are considering as K? Here this one, C by BAN. Okay, where K is equal to C by BAN. This K is called as, okay, this K is called as galvanometer constant. Galvanometer constant, or it has some other name also, reduction factor. K is the reduction factor or galvanometer. C by BAN is considered as K, then I is equal to K theta we write. That means if you will send the more current, then more torque will act. Due to the more torque, more deflection will occur. That means if current is more, then the deflection is more. The current through the moving coil galvanometer is proportional to deflection. That means if you send the more current, then the more deflection it will take. Then due to that it will show the more current. Based on the deflection we can measure the current. This is how moving coil galvanometer can measure the current. Okay. It was very simple. When the current carrying coil is placed in between the two poles of magnet, then on the torque will act. Due to the torque it will deflect. Then based on the deflection it will give some reading. Okay, like this the moving coil galvanometer can measure the current. And the voltage is, it was very easy to measure the voltage. Voltage is equal to current into resistance. If you multiply with the resistance, then automatically we will get the voltage. Okay, take the screenshot. And it was very important. Okay, and in this some extra points I am going to explain. What is the role of this soft iron? Why we are using this soft iron? What is the role of this radial magnetic field? Okay, that I am going to explain. After that, what is current sensitivity? What is voltage sensitivity? And on what factors they will depend. If we change the current sensitivity, then how the voltage sensitivity changes. These topics I am going to explain, and that is continuation of this moving coil galvanometer. And listen very carefully, and it was very easy and very important also. Okay, and now topic is what? Moving coil galvanometer. Take the screenshot and note every point. I am going to rub this part and then I will continue. Okay, look here. In the last term we got as formula I is equal to K theta. In that K is what you got finally? I is equal to K theta formula we got. Okay, in this what is K? K is the C by BAN. Let us go for the terms that are present in this. Okay, what is N in this? Number of turns in the coil, right? N is the number of turns in the coil. Okay, number of turns in the coil. What is A? A is the area of coil. If the coil is in rectangle shape, we write the area length into breadth. Okay, and if the coil is in circle shape, we write pi r square. B is the magnetic induction, external magnetic field. Magnetic field or induction. What is C here? C is already we know, that is torsion constant or restoring torque per unit twist. Now let us go for the one thing. What is the role of the radial magnetic field? role of radial magnetic field. We are using the radial magnetic field in this. What is its role? What is its role? Role of radial magnetic field. Role of radial magnetic field. The role of radial magnetic field is that the radial, due to the radial magnetic field, okay, due to radial magnetic field, what happens? Due to radial magnetic field, plane of the coil always parallel to magnetic field. Okay, plane always parallel to the magnetic field. Due to the radial magnetic field, the plane of coil always parallel to the magnetic field. Okay, radial magnetic field like this there, right? The plane of the coil like this there. This plane is now parallel. Okay, the plane of the coil is like this there. Okay, look at here. This is the plane of the coil. If this is the plane of the coil, okay, and this is the plane of the coil, and now the magnetic field is applied like this, then when you will rotate the plane of the coil, then also always this magnetic field parallel to the plane of the coil. Okay, with the rotation of the plane of the coil, okay, with the rotation of the coil, the angle does not changes. In radial magnetic field, always plane parallel to the magnetic field. Look at here, this is the magnetic field, this is the plane. Okay, this is the magnetic field, fixed. Magnetic field is fixed. Plane of the coil is rotating, right? Every time they are parallel, and plane and this magnetic field are parallel. What about the area vector? Okay, area vector means like this there. And actually deflecting torque formula NIAB sin theta, but in this theta is angle between the normal to the plane of the coil and the field. Normal to the plane of the coil is like this there, the field is like this there. That means we have to take angle as 90 degree. Angle is 90 degree. When the plane of the coil is always parallel to the magnetic field B, due to that maximum torque will act. Okay, and theta is 90 degree, the torque become NIAB, that is maximum, right? Due to the radial magnetic field, the torque become maximum. And the angle is 90 degree. Okay, right. Next, let us go for what is the role of the soft iron? We are using the soft iron, right? What is the role of soft iron? Role of soft iron core. What is the use of this? Why we are using this one? The reason is that the soft iron, when we will apply the soft iron, actually I say this is the soft iron. Okay, here one north pole is there, here south pole is there. These are external magnetic field. This is the soft iron. This soft iron always again, whenever the soft iron is placed in the external magnetic field, that soft iron also convert into magnet, and it also produces the magnetic field. That means the soft iron, what soft iron will do? Soft iron increases the strength of the magnetic field. Okay, soft iron, cylindrical soft iron core. Cylindrical soft iron core not only makes radial magnetic field, okay, due to the cylindrical soft iron core only radial magnetic field generates. Not only radial magnetic field, okay, and the strength of the magnetic field also increases. Due to the cylindrical soft iron core, okay, the field become radial, magnetic makes the radial magnetic field, and not only makes the radial magnetic field but also increases the strength of the magnetic field. Okay, not only makes the radial magnetic field and but also increases the strength of magnetic field. Increases the strength of magnetic field. Very important. Increases the strength of magnetic field. Okay. What the soft iron will do? Soft iron magnified, it will convert into magnet, and due to that it also produces the magnetic field. That's why the strength of the magnetic field will be increases. And due to the cylindrical soft iron only, radial magnetic field produces. That means there are two works are there with the soft iron core, cylindrical soft iron core. One is radial magnetic field, and other one is cylindrical soft iron core produces the radial magnetic field, and other one is what? Other one is to increase the strength of the magnetic field. And let us go for one more point, that is what is current sensitivity and what is voltage sensitivity, that I am going to explain. It was very easy and you listen very carefully, and it is very important also. And what is current sensitivity and what is voltage sensitivity, what are their units, and what is the relation between them, and what factors they are depends. Okay, the first one is current sensitivity, right? Current sensitivity. Current sensitivity. Current sensitivity is I suffix S. Current sensitivity. Current sensitivity. Okay, its definition is very easy. That is, I will tell, I suffix S is the formula for the current. I suffix S is current sensitivity denoted with I suffix S. That is, the definition is the deflection per unit current. The deflection per unit current is called as current sensitivity. Okay, deflection per unit sensitivity. Deflection per unit current. Current sensitivity formula is current sensitivity is equal to deflection by current. This is the formula for the current sensitivity. Then deflection per unit current, how to find out the deflection per unit current? We know the current formula in the moving coil galvanometer. That formula is C by BAN into theta. From this you can find out that theta by I. Theta by I we can find out very easily, that is BAN by C. Is it correct? You see here, current sensitivity is deflection per unit current. This is deflection, this is current. Deflection per unit current. Then deflection per unit current theta by I we write as BAN by C, we can take that side, then we will get this formula. Okay, deflection per unit current is called as deflection, angle of deflection by current. That is called as current sensitivity. And now what is voltage sensitivity? Voltage sensitivity. Voltage sensitivity. Voltage sensitivity denoted with V suffix S. Now that is very simple definition. The deflection per unit voltage. The deflection per unit voltage in moving coil galvanometer. The deflection per unit voltage is called as voltage sensitivity. Voltage sensitivity. Let us see, voltage sensitivity formula is what? Voltage sensitivity is equal to voltage sensitivity, that is V suffix S, is equal to deflection per unit voltage. Deflection by voltage. Deflection by voltage. Then how to write the deflection per unit voltage? Take the screenshot and note it. Right. Now deflection per unit voltage we can write as voltage sensitivity is equal to deflection by voltage. This voltage we can write as current into resistance. This is a moving coil galvanometer, that's why current into resistance of the moving coil galvanometer. Theta by Ig we write. Okay, then theta by Ig we write. But theta by I is what? Theta by I we write as where G is the resistance of the galvanometer, right? Resistance of galvanometer. But we know already current formula in moving galvanometer, that is C by BAN into theta. From this we write the voltage sensitivity formula as, in place of theta by I we write here. Okay, theta by I, what we write theta by I in this? Theta by I, from this we write as, from this theta by I we write as BAN by C. Is it right? Now here substitute theta by BAN by CG. Is it right? This is the formula for the voltage sensitivity. Okay, we got the current sensitivity formula and voltage sensitivity formula. Now I want the relation between the voltage sensitivity and current sensitivity. Relation between voltage sensitivity and current sensitivity. Okay, what is the relation between them? Then how to derive the relation between the voltage sensitivity and current sensitivity? Relation between voltage sensitivity and current sensitivity. Then what is the formula for the voltage sensitivity? The voltage sensitivity is equal to deflection per unit voltage, whereas theta by Ig. But what is theta by I? Theta by I is a deflection per unit current. Voltage sensitivity is equal to current sensitivity by G. Okay, this is the relation. We can also write like this: voltage sensitivity Vs is equal to current sensitivity by G. Voltage sensitivity V suffix S, current sensitivity I suffix S. Okay, and now I am going to continue. One small point I am going to give last, and then I will close. Okay, right. How to increase the current sensitivity and how to increase the voltage sensitivity? If the increase in voltage current sensitivity, okay, may not increase the voltage sensitivity. Okay, note, what you got the current sensitivity, on what factors it depends. Current sensitivity, that is I suffix S, right? Current sensitivity is I suffix S. Its formula is what? Deflection per unit current. That we got is, from that we know I formula C by BAN into theta. From this theta by I, what you will get? That is BAN by C we will get. Okay, and current sensitivity, on what factors it depends? The current sensitivity depends upon the magnetic field. If you increase the magnetic field, then the current sensitivity also increases. Area of cross section, and current sensitivity directly proportional to number of turns, and the current turn sensitivity is also inversely proportional to C. These are the factors on which the current sensitivity depends. What about the voltage sensitivity? Voltage sensitivity. Okay, voltage sensitivity is Vs, that is deflection per unit voltage. that is voltage we write as current into resistance. Here from this the voltage sensitivity formula will get theta by I we got as from this BAN by C. This is the formula for the voltage sensitivity, right? The increase in current sensitivity, voltage sensitivity factors what extra, the voltage sensitivity also depends upon the B, voltage sensitivity also depends upon the area, voltage sensitivity also depends upon N, voltage sensitivity also depends upon C, okay, and voltage sensitivity also depends upon 1 by G, right? These are the factors on which voltage sensitivity depends. Voltage sensitivity extra one term it will depends. Okay, the increase in important point I am going to tell one important point. One time it came in the exam. The increase in voltage sensitivity, okay, the increase in current sensitivity may not increase the voltage sensitivity. Actually, voltage sensitivity proportional to current sensitivity. But when the current sensitivity increases, then the voltage sensitivity may or may not increases. Then why? That I am going to explain. The increase in current sensitivity may not increase the voltage sensitivity. Why? Okay, because okay, when you will increase the current sensitivity, how you will increase the current sensitivity? Mostly we will increase the current sensitivity by using number of turns. We can easily increase the number of turns. When you will increase the number of turns, current sensitivity increases, right? Because current sensitivity proportional to number of turns. When number of turns increases, current sensitivity increases. But when number of turns increases, then the length of the wire increases. With that, resistance of the wire also increases. Resistance of the galvanometer wire, G also increases. That means when current sensitivity increases, then G also increases. Okay, right? That's when the increase in current sensitivity may not increase the voltage sensitivity. When you will increase the current, if you will increase the number of turns, then the current sensitivity increases. Along with the current sensitivity, G also increases, because number of turns you are increasing means wire length increases. Wire length increases means resistance also increases. Resistance of the galvanometer also increases, right? Then when current sensitivity increases, G increases, then the ratio is constant, right? The voltage sensitivity does not increase. That means the increase in current sensitivity, if it occurs with the increase in number of turns, then with that the galvanometer resistance also increases. Due to that, voltage sensitivity remains constant. This is the thing. Okay, right? Okay, the increase in current sensitivity may not increase the voltage sensitivity. Sometimes it may be increase the voltage sensitivity. When you will increase the current sensitivity, voltage sensitivity also increases sometimes. For example, you are increasing the current sensitivity by increasing the B. Current sensitivity increases. But at that moment, current sensitivity increases when you increase the B. But at that moment, G does not increases. Only current sensitivity increases. Then the voltage sensitivity increases. When you will increase the current sensitivity, sometimes voltage sensitivity also increases, but sometimes does not increases. Why sometimes does not increases? But when you will increase the number of turns, then the current sensitivity increases. With that, what increasing? Length of the wire, then the resistance of the wire increases. When current sensitivity increases, by increasing the number of turns, then resistance of the wire also increases. Then when these two terms are increases, the ratio remains constant. That means voltage sensitivity does not increase. The increase in current sensitivity may not increase the voltage sensitivity. May or may not. When you will increase the current sensitivity, it may not increase the voltage sensitivity, because two times I wrote here, because when the current sensitivity increases, by increase in number of turns, resistance of galvanometer also increases, hence voltage sensitivity remains constant. Okay, what I am telling it here, if you will increase the area, current sensitivity increases. If you will increase the B, current sensitivity increases. When at that moment the resistance of the galvanometer does not increases, that means when the current sensitivity increases, then the voltage sensitivity also increases. But in one case, when you will increase the current sensitivity, along with that voltage sensitivity does not increases. That means voltage sensitivity may not increase with the increase in current sensitivity. The case is that if the current sensitivity increases by increasing number of turns, okay, I will write here the increase in number of turns. If n is increases, okay, if n is increases and then current sensitivity also increases, I will rub here and I will continue. If n is increases, then what happens? Current sensitivity increases. Is it right? And with that G also increases. But the voltage sensitivity remains constant. It does not increase. Right? This is the point that I want to explain it here. Okay? Thank you for listening my class. Till now, if you not subscribe my channel, subscribe my channel. Share to your friends. Thank you.